Welcome, everyone. Happy Friday. It's almost the weekend. We are in the very final stretch of this course. As you know, our final exam coming up is like the first day of the exam period. So that means over the next 2 and a little bit weeks, you want to stay up with the content because we are going to be going right to the last lecture or two. So you want to know all of the content up until the next 2 weeks. It's a cumulative exam, so that means topic 1.1 gases all the way through the workbook. So today would be a good time, if you haven't already, to start reviewing that gases content, thermochemistry, thermodynamics, equilibrium, so that you can make space to learn the final 2 chapters on redox chemistry. We'll be getting very close to the end of that today, and then spending a week and a half on kinetics. So now's the time to be plotting out your time so that it's not a rush at the end. Chemistry is a terrible subject to learn last minute. It doesn't work so well. So it's much better to chunk your learning along the way. There are some extra review sessions being offered by Student Experience. So upper year students who have taken Chem 1302B are going to be offering some drop-in help sessions, some review sessions. This will be posted with the lecture notes this week. Okay, we're heading towards the end of topic 4.3, looking at electrolysis. Redox reactions that are not spontaneous, they have a negative cell potential, but we want them to happen anyway. So if we apply voltage, apply enough voltage to meet that cell potential, plus a little bit more for that extra overpotential, we can cause a non-spontaneous reaction to occur. And the chloralkali process is one of those really important industrial applications where voltage is applied and we can produce important reagents like chlorine gas and sodium hydroxide. Well, when we're applying voltage to make a reaction occur, we're applying voltage, it causes the flow of current, the flow of electrons. We can now quantify the amount of products that we could produce or quantify the amount of reactants that we need to make our desired products. So most often with a non-spontaneous reaction, we can apply voltage to produce something. Today we're going to calculate how long this process takes depending on the current that we're using. We've been balancing these half reactions. For example, aluminum 3+ requires 3 electrons to be reduced to aluminum solid. Well, if we want to produce 1 mole of aluminum, we need 3 moles of electrons. And the charge of 1 electron is really small. You can see the little negative sign there. It's an electron, it has a negative charge. But that's a really small number. So more often we talk about a whole mole of electrons, or 3 moles of electrons to make 1 mole of aluminum. 1 mole of electrons has the charge of 1 electron multiplied by Avogadro's number, which gives us 96,485 coulombs of charge for 1 mole of electrons. They're electrons, so we know that it has a negative charge. But sometimes when we talk about the flow of current, it can be a positive or a negative, depending on which way that current is flowing and which way the electrons are flowing. For our purposes in Chem 1302B, we don't really care which way the current is flowing when we're calculating the amount of time it takes to do this reaction. So in your workbook, you have this equation here on the right, where charge, which is Q, which is measured in coulombs of charge, the amount of charge, is the number of moles of electrons multiplied by Faraday's constant, which is 96,485 coulombs of charge per mole of electrons. And obviously, if we multiply that by the number of moles of electrons factor out. It's in the numerator, it's in the denominator, and we're left with charge, which is Q. Now, electrons have a negative charge, so we can put a negative charge there. But moving forward, I'm actually just going to use N times F. We know electrons have a negative charge. We're not going to pay attention to which way those electrons are going, so whether the current is positive or negative. So I'm going to be moving forward with this equation because it's not going to change what we're going to be doing with these equations. Well, this is one very handy formula to equate the number of moles of electrons to the amount of charge due to the passing of those electrons that we need to do this electrolysis reaction. Well, we have one more equation which is really helpful to solve charge type problems. And charge is now correlated to current and time. Now, current is measured in amps or amperes, and amps is equivalent to 1 coulomb of charge per second. So you can count the amount of charge that goes by in 1 second. That would be the current. So if we're going to multiply the current, coulombs per second, multiplied by time, well, time had better be in seconds if we want the seconds and the per seconds to factor out to give us coulombs of charge. So we now have two ways to determine charge: the number of moles of electrons in Faraday's constant and current and time. This allows us to correlate and connect and calculate moles of electrons to time and current. Moles of electrons from a balanced half equation are also related to the moles of reactant, or the moles of product that we want. So we can calculate some interesting problems based on these correlations. As an extra little note here, we've seen this equation before. Gibbs free energy is equal to the negative N times F, so the number of moles of electrons and Faraday's constant, which we now know is charge, times the voltage of that cell, and that will give us the energy in joules. So the energy in joules is equal to the charge in current times the cell potential in volts. And we can correlate these ideas to determine Gibbs free energy. We know that if we have a positive cell potential, we multiply that by the negative NF, that would give us a negative delta G, which tells us the reaction is spontaneous. A voltaic cell is spontaneous. An electrolytic cell is not spontaneous, but we want it to happen, so we zap it with voltage, we push and pull those electrons to make our desired products. So we're going to solve 3 problems that involve these types of equations. The first is a little bit theoretical, the next 2 are much more practical. In this problem, we have a current of 5 amps, and it's flowing through a metal wire. You could imagine that it's a wire that's connected to a battery. We want to calculate how many moles of electrons pass through a little cross section of this wire in 7 seconds. So we're going to pretend there's our eyeball, and we're going to watch and count the electrons that go by. And we know we can't actually do that, right? You can't go 1, 2, 3. That's not how we do it, but we can measure it in terms of current and time. I want to see how many moles of electrons go by in 7 seconds. Well, I'm given current, 5 amps. I'm given seconds. That allows me to solve for charge. If I know charge, and I always know Faraday's constant, I can solve for the moles of electrons. So let's go ahead and do that. Now the current is in amps, but for unit purposes, I'm going to show how my seconds factor out, which gives me 35 coulombs of charge, which would go by in 7 seconds. Well, 35 coulombs of charge is related to the number of moles of electrons that went by and Faraday's constant. Which tells me that I had 3.63 times 10 to the negative 4 moles of electrons pass by in 7 seconds. Now, most people that you meet won't care about that number. What we need to do is then turn the number of moles of electrons into something more meaningful, the amount of reactant that we need to actually put in the battery and sell to people, or the amount of product that we're going to produce during one shift that we can actually sell and make money on. So we're going to go to the next problem to see how this actually is relevant. This problem is about electroplating, and this is an industrial process that happens all over the world. And we've chatted about this before. If we want to buy a necklace or something, we don't want to pay the full cost of purchasing that amount or that mass of precious metal, we can buy a cheaper material that's just being electroplated in the precious metal. So just a thin coating of the more expensive material. Well, this thin layer of metal is being electroplated onto some conducting surface. Maybe it's a necklace. The object is the cathode. The precious metal is going to be reduced from an aqueous form onto a solid form onto this object. And we want to know what mass of silver can be plated out of a solution of silver nitrate if a current of 0.75 amps is used, and this experiment goes on for a whole hour. Well, the first thing we need to think about is, well, what's in this solution? What's being plated out? We want to examine the amount of solid silver that's produced, and we have a solution of silver nitrate. And you may remember from our solubility table, or you can look up in the formula sheet to find the solubility table. Any nitrate is going to be soluble. So this silver nitrate doesn't actually stay like this in solution. It goes to silver cations and nitrate, a polyatomic anion. These silver cations can then be reduced. And I'm just going to write out the half reaction because that's the only one that I care about right now. The silver cations can be reduced by 1 mole of electrons to make 1 mole of solid silver. We want to know the mass of silver that can be produced. So we need to do something with these electrons. Well, in this problem, we're told current and time, so we can solve for charge. Once we know charge, and we always know Faraday's constant, we can solve for the moles of electrons. Once we have moles of electrons, we can see that it's a 1-to-1 molar ratio of electrons required to produce 1 mole of solid silver. So given that, we can start our calculation. So we have 0.75 amps, or coulombs per second, to remind us that the units are seconds. But I'm told 1 hour, but I don't want 1 hour. I need this 1 hour time in seconds. Well, perhaps you know this number off the top of your head, and that is great, and you're welcome just to write it down. But for the rest of us, you may need to do some unit factor analysis, to solve for the number of seconds. Well, I want to convert hours into seconds. I know that 1 hour holds 60 minutes. If I stopped there, hours and hours would factor out, and I would have 60 minutes. But I want to keep going. I know that 1 minute contains 60 seconds. Minutes and minutes factor out. I'm left with the units of seconds. So therefore, 1 hour is 3,600 seconds. This is the time in seconds that I want to put in to solve for charge. And this gives me 2,700 coulombs of charge that will pass by in this 1 hour. I can now use my second equation to turn charge into the number of moles of electrons. Now, if I stopped here, I would have the moles of electrons. So that's good, but I need to get to the mass of silver. I can see 1 mole of electrons will produce 1 mole of silver. So because of this 1-to-1 molar ratio, I can simply say, you know what, the number of moles of electrons that I calculated is also the number of moles of solid silver that would be produced. If it wasn't a 1-to-1 molar ratio, I'd need to do an extra step. Well, I now need to convert the number of moles of silver into the mass of silver. And we can do this by looking up the molar mass on the periodic table. Therefore, during this 1 hour, I will be able to electroplate 3 grams of silver onto my necklace, or onto a boat, or onto a piece of machinery or tool. So through Faraday's law, correlating the amount of electrons to the amount of product or reactant, we can determine how much material we can produce, and now we can sell this necklace. Let's do one more problem now. This next problem is also about electroplating. Now we want to electroplate a specific amount of mass of copper from a solution of copper chloride, and we're told the current is 3.5 amps. We want to know, well, how long is this process going to take if we use this 3.5 amp current? Well, I have a solution of copper 2 chloride. It's going to dissolve. Something in that solution is going to let me make copper solid. If I can figure out the number of moles of copper in 6.5 grams, from that, I can figure out the number of moles of electrons required to get me to that 6.5 grams. From moles of electrons, I can figure out charge. From charge, given current, I can solve for time. That's my roadmap. So let's start by calculating the number of moles of copper. I did not finish these equations. That's for you to do in this coming up clicker question. So I'm going to leave that blank for just a second as we do this point in the calculation. I want to make or produce 6.5 grams of solid copper, and I know that 1 mole of copper has a mass of 63.55 grams. This is simply grams to mole calculation. This gives me 0.102 moles of copper. That is my goal for this problem. So my question for you, how many moles of electrons must be transferred to electroplate this 6.5 grams of copper out of solution? Okay, and 10 more seconds to get your answer in. And 3, 2, and 1. Okay, most people went for D. D is the correct answer. We had a lot of votes for C, so let's see how this is connected. to figure out the number of moles of electrons, we need a balanced half equation, at least. We need to figure out what copper 2 chloride forms. I'm going to get a copper ion with some charge and chloride ion with some charge. When chlorine becomes an ion, most often, almost always, it becomes a -1 oxidation state, or a -1 charge. And we need to balance this to have 2 -1 charges. Well, we can also even look at the oxidation numbers in the copper 2 chloride. Copper could have a +1 oxidation state. It could have a +2 oxidation state. Hope it comes back. And we need to figure out which one that is. If we have 2 chlorines, each with a -1 oxidation number, the sum needs to come to 0. We have 2 chlorines, each with a -1. That's a total of -2. Therefore, my copper must have a +2 oxidation number. Or when I dissolve it and make 2 -1 charged chloride ions, I only have 1 copper ion. It needs to balance the charge. Therefore, it must have a 2+ oxidation state. That means I need 2 moles of electrons to react with 1 mole of copper 2+. So if I have 0.102 moles of copper, I can do a mole ratio. There are many ways to represent this. This isn't the only correct way to think about this. But based on my balance equation, I need 2 moles of electrons for 1 mole of copper. I want to solve for the moles of electrons when I have 0.102 moles of copper. I can solve for the number of moles of electrons. I'm just multiplying it by 2. This gives me 0.204 moles of electrons. And this is why the next slide answer is 0.204. We need twice the number of moles of electrons as copper. This mole of electrons is the number that we use for our charge equation. So the chemistry part of this that we really need to think about is our stoichiometry, balancing those half reactions, figuring out oxidation numbers and balancing charges, and then it's a straightforward calculation. So let's go ahead and do that. Now we could stop here. We've used the charge based on the number of moles of electrons. We know the current is 3.5 amps, or coulombs per second. That's 5,600 seconds. If you're really familiar with seconds, this might mean something to you. For the rest of us who don't usually use really big numbers of seconds, we can go to minutes and see if this makes a little bit more sense. This would give me 94 minutes. This is a number I'm a little more familiar with. That'd be about an hour and a half. So if we wanted to do this experiment, electroplate out 6.5 grams of copper onto some important tool, therefore, it's going to take us 94 minutes. So we've chatted about voltaic cells, spontaneous redox reactions that cause the flow of electrons. Electrolytic cells are when we don't have a spontaneous reaction, and we're going to apply voltage to make it happen. This brings us to batteries. A battery works because it operates as a voltaic cell until it dies, and then we can zap it with electricity if it's a rechargeable battery, and recharge this battery. And we're going to talk about how that happens today, and then look at some important examples of batteries that we may use from day to day. There are two different types of batteries, primary and secondary. Primary batteries are not rechargeable batteries. They're single-use batteries. You plug it into your remote control, and when it dies, you dispose of it responsibly. Some of our first dry cell batteries were zinc carbon or zinc manganese dioxide batteries. We've talked about the voltaic cell and the Daniell cell, and that required big sloshy solutions and electrodes and salt bridges. For batteries, we still have an anode and a cathode. We still need an electrolyte. We still need electrodes. But if we're going to stick it in our remote control, we don't want to have a sloshy beaker of solution that's going to spill on your coffee table or your couch or your skin, especially when we get to strong acids and bases. So the dry cell was developed so that you wouldn't have to have these sloshy solutions. A slightly moist paste, when we choose the right reagents, can also create a voltaic cell, a spontaneous reaction. So the dry cell was one of the first commercial batteries. It's what made flashlights possible. You didn't have to have sloshy solutions. You could have these relatively dry materials. But they would form a little bit of gas, and they didn't last as long on the shelf. So then alkaline batteries were developed. Alkaline means basic, and alkaline batteries have potassium hydroxide in them, just a little bit of that strong base, and this helps to reduce the formation of side reactions in gas bubbles. So in an alkaline battery, we have zinc hydroxide and manganese dioxide, and based on this connection and the difference in the cell potential, we can get a battery of about 1.5 volts. And we can make it in different sizes, a double A, I have a quadruple A in my stylus here. We could also examine a silver oxide battery. You can buy these at like Canadian Tire or Dollarama. They used to go in watches, other small things. One of the materials is silver oxide at the cathode. And again, now that we know how to calculate standard cell potentials and cell potentials under non-standard conditions, we understand where these voltage measurements come from. It just depends what's acting as the cathode and what's acting as the anode. But primary batteries can only be used once. If you try to recharge a primary battery that was not designed to be recharged, and you stick it in a recharger anyway, you could cause a fire. And people have done this because the backwards reactions, the reverse reactions, can sometimes create other side products. They weren't designed to be able to move backwards and recreate the same materials. It can cause bubbles, it can cause fires. Don't do it. But we do have secondary batteries that were designed to be rechargeable. Spontaneous this direction, and then we can apply voltage, and it will go exactly backwards to recreate our reactants. And then we can use the battery again in the discharge way, and then when it dies, we can recharge it by applying voltage. An example of this is the car battery, the lead acid battery. We're going to analyze that. Here we have our nickel metal hydride battery, used in lots of tools, now a very common rechargeable battery. And we're going to wrap up with the lithium ion battery. So as we've mentioned throughout our conversation on redox reactions, when a battery is discharging, it's acting as a voltaic cell. It's a spontaneous reaction which causes the flow of electrons. And this is going to happen until the battery dies. And we all know what that is like when the battery dies. It's kind of disappointing. There are two ways that a battery can die. One is that the cell potential comes down to 0. Remember, we can calculate standard cell potential under standard conditions, and then we can calculate the cell potential under non-standard conditions, and this depends on the temperature and the ratio of Q, the ratio of products over reactants, the ratio of those concentrations. Well, if the ratio of those concentrations gets too far out of whack, the cell potential can reach 0. It doesn't mean that you've actually run out of your limiting reagent or your reactants. It just means that the ratio of those two concentrations, if you have two concentrations in that battery, have reached equilibrium. Q has become K. The battery stops operating. There's no impetus for it to go forward anymore. It has reached equilibrium, and you will no longer have a flow of current. That's one way a battery can die, when the ratio of the concentrations just happens to result in a cell potential of 0. The other is the more intuitive answer. You simply ran out of your limiting reagent. And depending on the battery, either one of these reasons, whichever one's first, is what is going to kill your battery. Let's look at an example of this. Here we have a voltaic cell. We simply set it up, let's say with some iron ions and a solid iron electrode, some cadmium ions and a solid cadmium electrode. We set it up, and spontaneously, electrons start to flow. We have reduction, we have oxidation. Spontaneously it occurs. Based on the difference between the two standard cell potentials, we get a voltage of 0.06. Actually, it's not standard. It's non-standard in this example. But we still have a positive cell potential. And it's going to operate until the voltage reads 0, because the concentrations of the two solutions are out of whack, or the limiting reagent is done. If this is a secondary battery, a rechargeable battery, we can come along, apply a power source, apply voltage, and push and pull the electrons and cause the reverse reaction to occur. When this happens, we're operating the battery as an electrolytic cell. Now it's not spontaneous, but we apply voltage to make it happen. So we have a voltaic cell, we have a dead cell, and then if it was designed properly that the reverse reactions aren't going to create side products and cause a fire, we can apply voltage and recreate our starting conditions. We're going to look slightly in depth here at one example to see how the battery can die by concentration change and how it can die by the limiting reagent being used up. Now, in your workbook, you have this example as well, so we're not going to do all the steps here. I'm just going to pull some of these numbers. 100 grams of iron is equivalent to 1.79 moles of iron. If we started with 0.95 moles per liter and 1 liter of cadmium, that would give us 0.95 moles of cadmium. So we're reacting 0.95 moles of cadmium ions, 1.79 moles of iron, and that's what I'm just going to pay attention to right now because those are my reactants. Let's say we started with a 0.2 molar solution of the iron and a 0.95 molar solution of the cadmium. We could calculate the non-standard cell potential based on the ratio of these not 1 mole per liter solutions and see that the cell potential is positive, and spontaneously it proceeds. As time goes on, the reaction, as written on the page, is going from left to right. The amount of cadmium ions is going to decrease, and the amount of iron ions is going to increase, because spontaneously it's going from left to right. Until, for this particular example, iron concentration increases to 1.1 moles per liter, and the cadmium concentration, as given here, decreases to 0.05 moles per liter. Now, they're not 0 yet. We can see based on the 1-to-1 molar ratio, we still have some solid iron, but concentrations have gone down in the reactants and up in the products, such that when we calculate the cell potential now, based on these revised concentrations, because we used up our reactant, we produced products, the ratio at this point, when we have a 1.1 molar solution and a 0.05 molar solution, the cell potential is 0. The battery stops operating. The battery is dead. That's the end of the story. Unless it's a rechargeable battery, and then we can zap it with voltage and drive it backwards. This is one way that the battery can die based on Q, the ratio of these solutions. The ratio is just such that the potential is 0. We still have materials, we still have reactants, but it doesn't matter, the cell potential is 0. That's one way for the battery to die. But what if we started with less iron? 24 grams of iron is about 23 or 0.23 moles of iron. And if we started with 0.95 moles of cadmium, and the reaction proceeds, same way as before, and it proceeds until it dies, because we've lost 0.23 moles of our iron. We have no more iron left. We've lost that same amount of cadmium. I don't think I have this number written down. Oh, I do. We still have cadmium left, but the limiting reagent is gone. We could still calculate the cell potential, the ratio between the iron 2+ ions and the cadmium 2+ ions, but there's no more iron. The iron is gone. The battery is dead. So 2 ways for it to die. We run out of something, or the ratio gives us a 0 cell potential. If we have a battery that doesn't have concentrations because everything's solid, well, it's just going to be running out of the limiting reagent. If we have solids and aqueous, well, something could run out, or the ratio gets to 0. So example 4.4.1 in your workbook is another example just like the one we talked about, but we just talked about it. So we're not going to talk through the same example again. So I'll let you review this on your own time. What I want to do is analyze this silver oxide battery. I think this is a more interesting example. This is a little button battery. We've seen it already. You can buy it at a regular store. This battery is based on the following redox reaction. Zinc with an oxidation state of 0, going to zinc with an oxidation state of +2. Silver oxide, silver with an oxidation state of +1, going to 0. Silver is reduced. Zinc is oxidized. It's a redox reaction. It's spontaneous. It causes the flow of electrons, and we can do something useful with this battery. This battery, based on its design and the materials chosen and the temperature, generates 1.5 volts of potential difference. Let's suppose that this battery started with 0.1 grams of zinc, 0.1 grams of silver oxide, and 0.1 grams of water, and it was used and produced 1 × 10⁻³ amps of current. How long can this battery last based on this rate of current? That means how long until the battery dies? Well, we could calculate the ratio of the concentrations, but they're all solids. This one is going to die because we run out of the limiting reagent. So this means we need to figure out, well, what's the limiting reagent? From the limiting reagent, how many moles of electrons were used up while that limiting reagent was used up? Then we have our moles of electrons, and we can run with it, like problems that we've done before with charge and current and time based on the number of moles of electrons. So I need to figure out which is my limiting reagent. I need to take these mass values, they're all small because it's a small little button battery, and convert them to moles. And I can do that using the molar mass. We've calculated the number of moles of each of the 3 reactants based on the starting masses. But now we need to figure out which is the limiting reagent, which is going to run out first. We pay attention to the balanced equation. It's nice that it was given to us balanced already. We look at the stoichiometric ratio, how many moles of each we need as the reaction proceeds, and then we make a decision. Sometimes we have to do a calculation to make this decision. Since they're all a 1-to-1 to 1 molar ratio, I can do this in my head, and so can you. So I'd like you to put up your hand when I say the reactant that is the limiting reagent. We're going to start at the top of the list. Who says zinc is the limiting reagent? Who says silver oxide is the limiting reagent? What about water? And definitely it is the silver oxide. It is the smallest value, but that doesn't really matter based on the stoichiometry. So this is the limiting reagent. I need to see, well, if I used up 4.31 times 10 to the negative 4 moles of silver oxide, how many moles of electrons would be transferred? Well, I need to do a little bit more critical thinking here. Based on the balanced equation, 1 mole of Ag2O, silver oxide, produces 2 moles of silver. How many electrons are being transferred in this reaction? Well, I could figure this out one of 2 ways. Silver goes from a +1 oxidation state down to 0. That's a transfer of 1 electron. But there's 2 silvers in the reactants and the products. So that means 2 electrons are transferred based on this balanced equation. I could double check with zinc. Zinc is going from a 0 to a +2 oxidation state. That means it has lost 2 electrons. We produced 2 electrons, we lost 2 electrons, 2 is the number. So it's a 1-to-2 molar ratio of Ag2O to 2 electrons. So the number of moles of electrons is going to be twice that value. Great, we now have the number of moles of electrons. I can pull out my 2 charge equations, the one that takes me from electrons to charge, and then from charge, using current, I can find time. So I'm going to jump to a new slide to make sure I have enough space. I know the number of moles of electrons from the previous slide. Multiplying that by Faraday's constant, which gives me charge. This is the amount of charge that can pass until this battery dies. And now using that charge, I can solve for time. This gives me the value in seconds, but the question asks me to solve for the time in hours. So I'm going to use my unit analysis. I know that 60 seconds is 1 minute, and 1 minute, or 60 minutes, is 1 hour. This gives me 23.1 hours. So that's how long this button battery can last based on this very low amount of current. So we can quantitatively analyze these batteries. We can calculate how long it can last until it dies. Or if we want it to last for this amount of time, how much reactant do we need to put in? We now want to discuss different types of interesting batteries. And we're going to start today with our lead acid battery. So hold tight, we're going to use our next 3 minutes. This lead acid battery was developed back in the 1800s. Back in 1859, by a French physicist, this very robust battery was developed. It's over 150 years old. But we still use it because it is so robust, because it uses materials that are relatively cheap and accessible. It has a low energy density. It's kind of big and kind of bulky, definitely not something that you put in your TV remote or in your back pocket with your cell phone. But for a car that's already big and heavy and bulky, it works. It's robust. It works in 40 degrees Celsius temperature and almost 40 degrees Celsius in London, down to cold temperatures as well. Each cell has a voltage of about 2 volts. And when we connect this in series, we know from physics that we can add those voltages together to give us an overall 12-volt battery. We can analyze the reactions inside this battery. What's oxidized? What's reduced? Why does it matter? We'll have to do that next Monday. Have a great weekend. I'll see you next week.